Okay, great. So welcome back, everyone. So I know it's a short lunch break, and we do not have a lot of lunch option here. So we may still have see the person coming back. Yes.
Give it 1 second.
Sure.
Okay, here we go. Now it's going.
Is everything working now?
I think so.
Okay, great. So let's kick off the afternoon sessions. So in the morning session, we basically want to give you a basic introduction about our resources and let everybody be able to start using our own tech with our studio, which I hope everyone can do that, and I find it's very easy and no problem to do it. In the afternoon sessions, we will be talking about more on how we can really utilizing the high-performance computing facilities for our computations. I think that's one of the reasons most of the people here want to hear and to learn. So I will give about like 30 minutes lecture slides about what are the approach we support to scaling up our computation at Tech here. Then the Riju will come here and give a more detailed walkthrough on how we can utilizing a package or parallel package which comes with our core distributions. Then between 2 and 3, we will do a little bit of hands-on lab sessions. We will just walk around, and if you have problems, you can ask us. And for people attending this online, feel free to ask questions through the chat window. Feel free to explore. It's basically free sessions, and you can try out the exemplar scripts we put out in the morning sessions or during the afternoon sessions. We will print out more examples out. Just give it a try, play with it, and let us know if you have any problems with them. It's a good time for you to try and because we can answer the question at once and on the spot. Then after people get a chance to get their hands on with the running R in parallels, we will have the last sessions where we are talking about more on how to understand the R performance, how to understand your code better, so you may utilizing the resources better, you may improve the efficiency of your program even more. So again, feel free to ask questions anytime here or through the chat channels. I mean, starting with the scaling up R and the computation. So this is R in the HPC is something quite new, not really new, but it's something happens more rapidly in the recent couple of years. At Tech and also at Exceed, and we have several partners in other institutions as well, is really want to push out more usage of R in the HPC environment. So we have really a fancy name and nice graphics made by the colleague from the Indiana universities, and we call it Super R. So we have been hosting a related workshop and the BOF sessions during the supercomputing in the past 2 years. So first thing is why people really want to using the HPC. So the R user is not a traditional HPC users. That's because like we get more and more sort of user questions on I have this kind of existing R solution I have been used in my lab for like 5 years. Now I suddenly getting this big data set, then I use the same solutions. It used to work, but now it breaks in every way. So it typically could be runs out of memory or runs out of days without finish. So that's a case. Most users, most users come to find us, that's where we can really help out with those kind of the computations. So over the years, basically we have been utilizing sort of 3 strategies and in terms helping and solving that type of questions. The first one is we want to utilize the latest hardware technologies, and there's a lot of like what we call the massive parallel hardware, where they offer a lot of additional processing core. Even each core is less powerful than the CPU core you can find, but they have many more of them than you could afford in a single node. So those gives very nice parallelism to some computations. And more importantly, those kind of parallelism you can basically get for free. You only involve very minimum or no code change with your existing R solution. You can utilize them. So if your workload fit in that, that would be the easiest solution we can offer. Then the second one is to try to break the big computation with multiple jobs and just basically breaking them into small batches. So in the past, we have been done this. We have customized the scripts helping people to schedule their workflow so they can, instead of doing one big computations, we can make it as many smaller computations and run in parallels. Now we have these new resources coming up, and we are going to offer new ways helping people to ease that process and be able to break big computation easier. The third strategy I've been offering is to working closely with users and trying to developing a new parallel code based on their existing solution. So that's usually need more sort of in-depth collaborations and close work with users and developing something new. So let me briefly cover all three and give you some example or some ideas on how that works and whether you can think of if you have a solution, you have a problem, or you have some particular challenge today, what kind of solution may be best for you. So let me start with the hardware accelerations with the computational offloading. So as the first session I mentioned of the day, I mentioned that one of the features in the Stampede and the Maverick we want to let everybody aware is the Maverick, the Stampede has an Intel Xeon 5, which is a co-processing card. It offers like 61 additional cores on one single card. And also both Stampede and the Maverick has equipped with a GPU card for general purpose programming as well. The hardware, so the both Stampede and the Maverick has this kind of hardware support. So if your code, whether R or not R, can utilize those resources, that would be great, and we can you can get additional performance benefits. Back to R is there's two particular things we can support, and you can utilizing them fairly easy. One is for the my card, you can do it through the Intel math kernel library, what we call the MKL. It's actually a commercial library, but we have license installed on Stampede, so you can use it if you're doing work on doing computation on Stampede. The other package called Hypler is another open source package that developed for is kind of R package that used to let R to utilizing more on the multi-cores available per node and the GPU card available on each node. So there was a question on to do this kind of offloading if you want R to do some computation on those kind of card, whether we need to do it on compiling time or not. So this slide is actually explaining that questions better. R is something like we call the interpreted language. So what the end user developing usually is R scripts, and you define those functions. And those functions go through the interpreters during the runtime. It's converted into binary code for the executions, and typically those code will call a pre-built library. So that library is something we already compile and link and works on our system. So as an end user, you don't need to worry about that kind of compilation problems. To the Intel Xeon 5 card, which we refer as MAC, how the MKL can utilize this is the math kernel library is a specialized sort of the library that providing a lot of linear algebra computation support. So typically your R, if you do it on your own laptop, it may be linked to this library called BLAS for those kind of computation on our machines, and we can link them with BLAS, and we can link them with MKL. If we link the MKL, if we have the mic card installed on the same node, then a benefit of that is a lot of code can be automatically, like linear, especially in algebra related computation, can be automatically done through MKL on those mic card. So speaking of that, so I have to talk about something a little bit boring about the job submission process. So far in the morning, we have been trying to make things fairly easy, so you can go ahead to the Wait portal and to submitting, to click buttons to initializing our RStudio sessions. But if you need to using the parallelisms, you can still do some of them with RStudio, but for some of them, you may have to log into a remote console, log into our login node, and then do a job submission where you essentially tell our cluster, say, I want to run this. Then it will be placed in a queue, and at the time when the cluster has enough resources to run your job, then the job can be run. So for that type of job scheduler, at Tech, we're using something called Slurm. It stands for Simple Linux Utilities for Resource Management. This one is a sort of architecture view. So this kind of user command can execute on the login node. Then you send that command to our the Slurm node, and then Slurm will distributing that workload on the compute node. So that's basically how the job submission works. You're submitting a request, wait for that one to be executed, then later you can get them. So back to the users is to do the job submission, you need something. You actually just need one command line called sbatch, then followed by your job submission scripts. The job submission scripts is a text file. Here is an example. That's all the job scripts for the simple examples. It's a bash script, so it's indicated by the first line. So after that, you see a lot of like hashtag sbatch. All those lines are sort of the configurations per job. This is a medium site. There's more information about them. You can get more information through our user guides, either from Stampede and from Maverick. They have more user guide on that. But typically, the important things, the first one is your job name. It's more like descriptive informations. And then the -n is specify how many cores you are requesting. So on Stampede, we typically supporting this we assign resource per node. Then each node has a minimum of 16 cores. Then the -p is a queue name. It's a partition on which kind of resource available. It's like which queues your job will go to. Then -t specify the runtime. So typically we'll have limits depending on different queue. We have time limits how long your job can run. I think some is 24 hours, some queue is 8 hours, depending on the type of jobs. You can go to the user guide to getting more information on what are the queues available and what are the limitations associated with each queue. Then this reliance is it can automatically send a user a notification when your job is running or when your job is finished. And then the last line is actually what kind of thing you want to run. So basically those lines with hashtag is help you to setting up what kind of tell the Slurm daemons which kind of jobs you are trying to run. Then the last line is the actual jobs you're going to run. So we will have some exemplar job scripts you can submit, and you can look into it. If you have more questions on this, feel free to ask us or go to the user guide to get more details. I'm going to skip more details about it because I want to show. Say, for example, if you want to utilize the mic, it has to be something need to be set at the time of the submitting the job. So the node, the new you are going to use in the mic job submissions. So here is the actual job submission scripts for to utilize in the mic. This is the same hashtags sbatch. This helps to setting up the cluster, setting up the job, and tell the daemons what are the job configuration it is. The first batch of things is load a corresponding module that necessary to run that jobs. And all the lines I'm highlighting in yellow is a mic specific parameters. You need to specify. It basically tells how much work you want to offload to mic and how you want to utilizing them. Then the very last line is actually you execute our script and need to run one of your code. So in this case, I'm using a very well-known benchmark to benchmark our performance. So if you're not using the mic, basically you don't need to worry about those yellow line, and you can just directly, well, once you fill in this top part, and you just give the R scripts and then your R script to run, then it it can be submitted as a job to the backend, to the compute node, then to run them. So to do this, to do the mic offloadings, you just need to reconfigure, just to make a corresponding job submission file. You can run whatever R code that currently runnable with your own computers. If they are using the linear algebra computations like matrix operations, those kind of operations will be done if you enable mic, will be done through the mic. Any questions about that? So that's about how you use a mic, and the other package to use that is a Hypler. It is a package developed in Europe, I think. It consists of two parts, and one is more customized and one is more easy to use. And basically, the Hypler is supporting both multiple core per node and additional accelerator card like GPU installed on the node. The Hypler works a little bit different than the mic. In this case, you do need to go into your code and do a slightly editing of your existing code, be able to utilize them. So suppose this is a simple R code, and basically the first line define a matrix is a random generated 2000 by 2000. Then you do another one, you have two matrices, and you just do a matrix multiplication, and then we calculating how much time it's spending. So if you just run this, so this is a very simple, straightforward R code. If you run this, and the system may say, oh, it's taking 8.8 total times for this particular thing to finish. And to using things like Hypler to use like GPU, you actually just need to say first you need to load that libraries, and then you need to add a program to tell it you want to using the Hypler B model for the subsequent computation. Then the Hypler package will translate those and to make them runnable with the GPU installed with the system. So if you just add these two lines and you do the same run and submitting them, you can see you get almost like 8 times time saves on that, because some of the computation is being like the matrix multiplication is one best examples you can do with the GPU, because to best utilizing the massive parallelism offered by the GPU and the mic. So if you do some other computation, you may see that magnitude of improvements, but there are performance benefits to it you can easily get to just by calling those packages. So we have been doing some performance benchmarking with both mic and the GPU. So the R benchmark, it is a set of scripts that runs through like 15 different tests. It has been around for like 15 years almost. It's used for people to see what kind of R performance it does. So it's considered like the last two is just the sum of the total time and spending. And in this graph, it shows the speeding up based on each different test. You can see some of them we have the benefits by using mic or GPU. Some of them we do not have mic and GPU. It depends on the type of task. If they are more associated with large matrix operations, then typically you can see more speed up than the others. So the general advantage of this kind of the scaling up is there is really no or minimum amount of code change. The user can easily run their existing solutions with additional performance. So the other things we have been doing for quite a while is helping user to break the big computations by a batch processing. So basically we are we have done a couple project in collaborating with user before. So it depends on the actual workload, and sometimes we have generalized the scripts that can help, let's say, if all your data is reside in a different file, then we can run them differently, and our scripts can streamline that processing to submitting a batch processing of all those of entire directory. And recently, we are going to supporting R computation over the Hadoop and Spark. I mentioned the Hadoop and Spark very briefly in the morning session, and then we have 2 new clusters that begin to supporting this kind of the programming models. So basically, the Hadoop and Spark, they all based on same concept on breaking the big data into smaller chunks, then we can run the analysis on those chunks separately. Then later we can combine the result together to getting the full results. A typical example of the MapReduce is you have some input, and then the resource will automatically mapping your input and splitting them and maps them into different workers. Then the workers do the computation, then sending them out to the reducers, and then the reducer will assemble all the output from all the research, all the mappers, then getting the final result out. So apply this to R. It is really just instead of the mappers, the mappers can be a C program or Java program. It is native implemented in Java, but it supports all kind of interface. So R is one of it. So there's a package called R Hadoop and Spark R that can help you. You can define those type of the workflow and within R and running them through and utilizing existing Hadoop or Spark clusters. This is not something you can practice today. I want to introduce them to you, and this is something we are begin to support. And unfortunately, you cannot try this with the Stampy or Maverick. It will be you maybe in the future we can have a training session on when Wrangler is available. We can have people actually try to using them. But if you feel you have a very big data you want to process with R, feel free to let us know, and we can get you on with one of our resources like Wrangler or Rustler, so we can testing out your problem with the R Hadoop or Spark R approach. So here's one example. It's my colleague is in the Indiana University has been doing. So they're using the same kind of ideas, and they have a project with the HTTrust and to processing all their documents. So they define this workflow and to feed all the documents through the Hadoop clusters, and then do the processing and with R and putting the result together. So the advantage of this is you can utilize the existing R code, and mostly the job split and job staging can be done either manually or through things like Hadoop. But the limitation is a lot of the R code may not be works that way, especially if you run things like simulation-based analysis, or you need just do a lot of upsampling, bootstrapping type of thing, and then Hadoop or Spark may not offer you a good solution that way. So that brings us to the third approach we can apply to parallelizing the R is to utilize the parallel packages. So there's core package and there's a data mining package. There are also like hundreds of them packages that can help you to write a parallel program within R itself. This graph is made by one of my colleagues in the National Institute of Supercomputing Centers. He has done a lot of work. He's one of the main developers on the PPDR here. That's one thing we support is the PPDR, and also the latest version since the 2.5, R2.5, the parallel package has became part of the core distribution as well. The parallel package essentially including both multi-core package and the Snow package functionalities. So that's a thing the Reid will walk through, give you more details. Just in the higher levels, the parallel package basically contains two components. One is called the multi-core. It's used to be a separate package. The multi-core package allows users to be able to utilize the multiple core available inside the node. So the typical way of how parallel package works is in the basic introduction section, we introduce an apply function, an lapply function. So the multi-core package is basically one way to use it is just you need to find the corresponding function that supported by the multi-core package. So for example, the lapply became to MC lapply. That if you calling this one, then the computation will be done over the multiple core. If you do the default lapply, it will be done just over one single processing course. There are also other functionality that multi-core and Snow support, so you can actually write in more efficient and more detailed, go to more fine control on how the parallelism can happen. So the main difference between multi-core and Snow is multi-core by the name is specified, so it's working with multiple cores, so it doesn't really works well across multiple nodes. So SNOW, the name is the SNOW stands for Simple Network of Workers, something like that. It's a sort of a higher wrapper on top of another package called RMPI. So it supports distributed computing over multiple nodes. So the typical workflow of SNOW is your user need to first define what's a cluster to be used with SNOW. Then you have a corresponding function like the parallel iSupply instead of normal iSupply to be used with it. So the advantage of this approach is that you can do basically whatever you want and whatever the parallelism you have in mind, you can try to implement it yourself. And usually this may give you the best performance because you can really go into the code and to optimizing everything as best as you can. But on the other hand, is the disadvantage of this is if you're not a very if you're more like domain researchers, you do not want to invest in so much time in redeveloping the code, you may not want to really like this approach because it sometimes really gets into boring details about programming part. So with that, I will turn to the Riju, and today we want to go over more details on the parallel package, how it works, and how you can run them. And we have a few examples we put in the same example directory. You can get if you haven't get them. You can try those parallel packages along the example we talked about in the morning session during our live session in the afternoon as well. Okay. Click the hide this first. Okay. Let me check. It's maybe better start with HTML version. Okay. This looks better. Yeah. We can maximize this. In the training material, there's a RMD file, the R-Markdown file. Actually, you can upload it into your home directory, and then you can use the neat HTML to generate the document and run the code together simultaneously. But it will take some time, so I stop here, and I already generate the HTML. So that's the file you will generate after you run the other Markdown. So basically, I introduced several packages for the parallel process. So the first one would be the parallel package, and then the SNOW package, and then for each package. So if you want to run your code in the TACC resource, you have to understand the resource requirement for your program, especially those sections that dominate the time to completion. So most of the time, this code are balancing parallel, so can be split into simultaneous execution. So for the first part, you can copy this part into your RStudio and try to run it.
And then this function only define a my process, which randomly generate large vectors from a normal distribution, and then sleep 2 minutes, 2 seconds, and return the sum of the vector. So for this process, we want to know how much time and resource we take. So you can copy this part to run it, and then copy the process time minus the previous time. And you will get, actually you should copy the upper part and the lower part together into your RStudio, and then run these 3 lines together. You will get the time we need to finish the process. So you get approximately 10 seconds. And when you use the system.get process ID, you will get the ID, the process ID for this process, which run on the machine. So then we use the system command and actually call the top command in the slum. So you get all the process you're running on the machine. And for here, you only can see one R process here. So when you see this process, it's the actual process running on the tech machine, and it uses about 800 megabyte memory, and it takes about 8 seconds here. So right now, you know the actual memory used on the machine is about 800 megabyte and take about 10 seconds. So we try to do a for loop for this process, and then you can copy this part into your RStudio. And when you run it, actually you concatenate the results into a vector. So actually run 10 times of the myProcess function. So you can see how many times it takes to finish 10 iterations. It's about 28 seconds. And if you type the results on the RStudio, you give you a vector with 10 numbers. There's a question?
Yes. I have a timer to run. Yeah, it was just a copy. Yeah, I just copied it. Yeah, you can actually open it.
No, I haven't opened it. I opened it in test render. Because if you call from PDF, then what is this?
Right. Yeah, where did you get that from? Oh yeah, we have it online, right?
No, I have RStudio installed locally. I
Right.
copy here. Then
Oh, you should run those code on the RStudio on the BIS portal rather than your own RStudio.
It would be nice. This R Markdown file is on the folder we can download.
Yeah.
There's in the folder. You go to the tech website, and then there's a training.
Yeah, but this is not in somebody's like working folder on that.
So I put that 2 files also in the slash works, the directory, the place you copy the example data in the morning. So go there, there's a new folder called RHPC.
Okay. Yes,
and go in there, there's a parallel.rmd and parallel.html. You can open that one from your RStudio sessions on my
Yes, materials.
The R file.
Yes, the R markdown file.
So where you place your my example? Where you place your my example? You haven't given permissions.
I give him permissions already. Yeah, I can. Thank you. So for the for loop, it takes about 28 seconds. And we're trying to see whether the apply function will give us some better performance, because the apply function actually uses the vectorizations, so which would be make the computation more faster. So you can copy the code, the section from here, which actually equivalent to a for loop from 1 to 10. This would be a vector 1 to 10, 1, 2, 3, 4, 5 to 10. So actually, this function would apply 1 to 10 times my process. When you compare the for loop and the apply function, actually take not too much difference, and only use a little bit time to finish the process. And the memory would be a little bit less than the for loop. So for the for loop is about 800 maybe. So when you finish the apply function, we can go into the how we plan the parallel on the tag resource. For example, if you want to run 4 processes in parallel, assuming we use a machine with 8 GB and then 4 cores. So we use the 4 times the 800 megabyte. That's the memory we use for my process. That we end up with 3.2 gigabyte. If we want to run 16 process, then we need 12.8 gigabyte. And this is larger than the resource we have for our hypothetical machine. So for tag resource, it's better to assuming you only use less than 70% of the entire node's memories. So when you want to run 16 processes, you only want to use only assuming you have 8 GB on a machine, that means 8 times 0.7, you get 5.6 GB, and then use the 5.6 GB divided by the 800 megabyte. You actually need 7 cores to run the process. And this is the first parallel package we'll use, and this also is the easier one to write. So actually, this function using the forking to spin out additional R process, and it's only available on the Linux-like resource. So first, you need to do is to load the library called parallel. Just type, copy and paste this require function, and then load the library. And then you can try these sections on your RStudio.
What's the difference between require package and library package?
There's no difference. You can type library and the parallel or require parallel. They're the same, actually. So right now we can see the running time for the 10 iterations only use 8 seconds. So compared with the previous for loop, we use about 28 seconds here. So that means actually you use like 4 cores running the 10 process simultaneously. So for example, you send the first 4 process to 4 core. And then after you finish the first 4 process, you send another 4 to the 4 cores, and then finish the 8 iterations, and then you use 2 out of 4 cores to run the remaining 2 process. So when you look at the R process here, then you can see the 4 R sections running on the machine. So actually there are 4 cores. So the difference between the first two R section and the last 2, because 2 of the 4 cores must finish the remaining 2 process. So that's why you get more times on these 2 cores than the other 2 cores. And for the second package, parallel package, we use the Snow package. So the Snow use either MPI or socket based on the basic connections to achieve parallel. So that means you can use core, either multi-core on the local or remote machines. But it needs a little bit work to writing up the code. So for the parallel package, the Snow, you can load the package, like typing in library or require Snow, and then you load those functions into the RStudio.
So it says these functions are masked by the parallel package.
Yeah, that means some functions are override those existing functions. And this.
Okay, so previously you load the parallel, then you load the Snow. When you use example like class apply function, which package does it come from? Come from Snow or parallel?
The latest one, we always override the previous one.
Okay.
Yeah, the parallel package is actually relatively new, and it took the multi-core and it took the Snow package, and it just kind of combined those into this parallel package. So from your point of view, you don't have to really worry about it. They actually both provide some of the same pieces of code.
So these are the exact same functions.
Essentially, yeah. Best practice now is to use parallel, just because that's the one that we kept up to date.
So for the first line, you just replicate the local host 4 times. It will give you a vector of 4 local hosts. And then use the local host, we make a sub clusters. So after finish this step, you can actually type clusters in the command line to see what's coming out. And then there will be, you can see like 4 local hosts. And then we use the cluster export. You actually export the my process functions in the list. You can export many functions in the list to the global environment on the node or on the core. And then in this step, you can copy and paste these 3 lines into your RStudio. And then for this example, you also run on the local machine for 4 core. So it takes about 8 seconds. It's the same as the previous one. We use the MCL apply. So that's the second example, use multi-core. The third example to use multi-core, you can use the for each library and plus the multi-core. So the for each function is, you can make the parallelism easy to understand, and you don't need to understand. You don't need to know what are those MPI passing under the hood. So when you look at this example, you just need to load the library for each. The for each library is like a for loop functions. And then load the do multi-core library. and then copy this part into your RStudio. So you notice there's a do part here. That means you would do these 4 iterations parallel. The percentage do and then par percentage here. So if you only put the do percentage do and then percentage here, that means they will run these 10 iterations sequentially rather than parallel. So for this for this parallel on the multi-core example, you also take about 8 seconds. So this is the third examples to run on multi-core. And the last one to run the 10 iteration on multi-core is you can use the for each function plus no. That is equivalent to the previous one. The only difference here is the register and then do no function here. And then you can try copy the whole sections here and then see how much time you use to finish the multi-core parallelism. And the last example would be you can send in this process to multi-node and multi-core. So first you load the for each library and then do no library. And then there's a no list text file, which has the no names on the text file. But this example may not run on your RStudio right now. I will give another example which will assign 2 cores and then collect those core names into a text file later. So for here, you replicate the 2 nodes in the text file, and then each for 4 times. That means if you have 2 nodes called C1 and C2, so this function will give you a vector like C1, 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 C1 for C1, and then C2, 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 C2. So that actually give you like you can run you can make the subclusters on actually 8 cores on 2 machines. So each core only run 4 processes. So this part will be the same as the previous example. So another easy way to run the MPI process across multi-node is to use the wrapper MPI node. But for this one, there's still some problems you may get from the program, the machine. So, and then for the Slurm script, you can see here is the most important variables here, and it's like this the little m, that means the total number of MPI tasks you want to request. And then the big M here just specify how many nodes. So if the little n is 8, and then the big M is 2, that means you run 4 processes on each node. To give you an example, you can go to the terminal. Now you can copy the Pi example from this directory to your home directory. So the pi example actually used the Monte Carlo methods to estimate the pi. If you want to know the theories behind it, you just Google Monte Carlo methods, and then you can see here how to estimate. Can put it on the top. Is there any problem copying file?
Can you put them in a wages directory so they can all get it from the same place?
Okay. Just get permission. What's that we just Control C? Just type it.
你上面的，你某一层是不行的。You cannot to this. 哎，你是可以的。
对啊，我已经改了。
啥呢？
还有example。
这个就是一个口子在这儿。work。
studio sessions.
是这个。
Yeah.
你看它衬着是你 home， 你不用衬着 home。It should work now. Just try the copy from the reduce again. 在哪儿呢？拍，你看看那个。
Can you increase your font, Fusion?
Okay. Wait.
So if you still have trouble to copy the Pi example, it's also in the same path you used in the morning, but under that there's RHPC folder. Now it's also in the RHPC folders.
So when you finish, you can look at the Slum script. When you use the cat run pi parallel and then Slum script, you can see, yeah, you just cat run pi. If you want to change text, just use the VIM and then run pi. That's the hard way to change the text here. You probably cannot see. So it's better to change the email. Otherwise, I will receive many finished email from after you run the Slum script. So please change the email, the mail users here. You want to change it easily, you just open this file in your RStudio. You can actually use the RStudio, open the file. The Slum file actually is a text file, so you just file and then open file and then look for the run pi parallel. Can you see?
I think for theirs, that may not work because to load RStat, you have to have a certain version of Intel. I'm not positive. It depends on their environment.
Okay.
We'll just have to see.
Yeah, let me see.
That may get a warning message.
So after you change the email to your email address, so we can run the submission script as batch. Then pi run pi.
You might also need to change the project name.
Okay.
Using attack training or
You also may need to change the here into your project name. What's the project name?
So the product is different for type user account and the powerful receiving account. So you contribute to the training HPC.
Yeah, all caps just training -HPC.
Change it into training dash HPC. Just a dash A and then TACC dash DIC, change it to training dash HPC. Training or in cap. Instead of name on training dash HPC.
Stands for hash users.
Change the tag dash DIC into the training HPC. So when you're doing it, if you finish, you can look at the pyparallel.art file. It actually require for each package and do snow package. And the py function vectors actually randomly generate the xy coordinate for those points you want to place into a square. And then if the point falling into the circle, you give the value vector 1. Otherwise, the value would be 0. So at the end of the function, you would sum up the point, the 1 values in the value vectors.
Oh,
Oh, yeah, sure. You can't launch it through HTTP. You have to be doing this.
So the parallel pi is used for each function,
Yeah, she's actually on the login.
which run 16 iterations. So on 2 nodes, and each node run 8 process on 8 cores together. So then after finish the 16 iterations, you will sum all those 1 together. If you're not familiar with the pi example, you can go to the multi-color methods here, and then to see here how to estimate pi using the multi-color method. Actually randomly placing points in a rectangle. So for the parallel pi, equivalent to place 16 layers of this rectangle together. So when you lay them up together, you can measure the pi more accurate than only use 1 layer.
So there's a Windows node running on those nodes. There's your RStudio session.
When you finish all this, changing email and then changing the project name, you can submit the PyParallel example using S-batch. Then run pyparallel.slum. And then you submit the PyParallel example to the Stampy. And then when you type SQE, you can see it's actually running on 2 nodes. The first node is 41A and it's 202. You may have different number, different node. So these are 2 nodes that are running. And then you can see the process ID here, the job ID. And then you want to see the result, just cat pi dash out, and then input the process ID, and still running. So actually you can see the machine, the node numbers here. So there are 8 process running on the same node using 8 core. And then the other 8 process running on another node, 602, and using 8 nodes. So it should be finished. So right now, you estimate the pi. Here is 3.141654. And then the time to use it is 9 seconds. And there's another example you can run, is the sequential example. So it just runs 16 iterations sequentially. You send me an email when you finish. So this sequential example, you run it, you should need like 2 minutes, 2.5 minutes. We type the SQU GUE and then U-U user. And the submission script only asks for 1 node here. So you can see you assign 1 node here for the sequential task, and then only use 1 process.
How long were you in that?
So it's still running. So when you compare the sequential example and the parallel example, actually running 10 iterations, 16 iterations. So they should have the equivalent accuracy at the end, but one take longer. The sequential one will take about 2.5 minutes, and the parallel one only take 20 seconds, because you use 2 cores and 8 process on each core. So right now it's finished in about 140 seconds for the sequential pi estimation using the Monte Carlo methods. So you can change those like iterations here, change into larger number to make the estimation of pi more accurate. or you can distribute it to more nodes using more cores on each node. I think there's some successful example. I received many emails. So they didn't change the email. So actually runs successfully, right? Because the running time was 2 minutes. If you want to see if there's an error message, you can type I. If there's some error, you write into the text file. Just change the out into error, and you can see is there any error message inside the file. So sometimes you just write the low package, some information into the error text file.
That's actually the story. That is running time. Yes. Yeah. I'm sorry? Yeah, so there would be a PD if it was still waiting in the queue. So it's running, it's been running for 8 minutes. This one's been running for over an hour. Yeah, you're running a multi-node job, so you actually see which node you're actually running.
So it's a time out in the all file without the time. This one is execution out, it has a time. But the other so is a time. I think it's starting is still so the parallel is still running. Parallel should be faster. So the parallel takes
Should
longer,
be faster.
but it takes longer to run because my sequence already finished.
So sometimes you the resource allocate those nodes.
Okay.
If you cannot find two nodes, allocate the resource, you wait.
Okay.
So sometimes you know you actually not money.
Okay.
Yes, you can see sometimes resource allocation just with resource. Yeah.
So this time the parallel I use two nodes.
Yeah.
So suppose you just take half the time in sequential.
No, half the time you use two nodes. Also use two nodes. Within each node you use a core.
Okay. So I have 16.
Actually, should be 16.
Parallel.
Yeah. 1/16.
Okay.
Yeah.
That's not parallel. Can we use empty parallel?
It's not package.
No, the parallel. Let's say they use OpenMP or MPI.
API.
Do you have, this is local version of our studio?
Yeah, this was
Do you have it automatically? Like when you make changes there?
I just show the code here.
Yeah, that's what I
Yeah.
Right, yeah, that makes sense. Some people are trying to run a Maverick though, so they have to use this key there.
So here's my question. Which one between those slides?
Each one can see as a computer and for the laptop. You have 4 cores, right?
Okay.
So each core can process one process. You have 4 cores, you can process 4 processes. 4 threads together.
So this node, the node control threads.
Those processes and threads.
Process and thread.
Yeah.
Okay.
You can do this process use each CPU one instructions.
So what is node?
No, it's can see your computer as a node.
Okay.
There's a it's
And my computer has
you should have 4 cores, right?
okay. Yeah.
So you can handle 4 processes.
Okay. Okay.
There's the difference. If you want to use 4 cores, that's all you just use the replicate localhost 4 times. Then you can use 4 cores.
And most programs now not only use one.
Yes.
Okay.
Use the level package.
What's the directory of the code? Can we know? You're working from?
It's already copied into your home directory.
Oh, is it?
You have to copy.
Okay. Good.
Directory should be there's the directory you can copy.
Thank you.
Just 4 files. There's a command to copy to your home directory.
There was, in addition to the email address, we're supposed to change the allocation.
Yes, change the allocation TACC, DIC into the training HPC. So here you have to change the email into your own email address, and then change the project TACC-DIC into training-HPC.
Try ls minus space.
These two lines. Change.
Oh, that's right. So we're all sending you emails. That's
Yeah.
what's happening, right?
You can send me email. I know your success.
That's how you get graded. It's an email from him.
That's right. You fail automatically, right?
You fail, I would know it.
All right, 1 second. Okay, for each, depending on which module we're using our stats, it should be smaller there.
Do you want to see context? Folder.
Yeah, you just
If you want to make a folder, you can make it. But you have to type. When you run the some script, you have to type the folder.
Can I ask you a question?
Yeah.
I don't know if I'm not getting it. Sorry,
What do you need to change other than the email address? On this, there's something else?
You cannot see it?
I just don't see what we are supposed to change other than the email address. Just an email.
And then the project name.
Those are correct already.
If that's the correct one.
That's the one you need to change.
To what?
Oh.
To what?
Change the TACC dot that dash DIC into the training here.
Oh, training?
Training.
HPC?
HPC.
Oh.
Spec the right now there because I think this might still be in share on the.
So I need to
Just write down to the chain paper on the entire grid chain -8. Just write the entire thing.
just want to see how many of them success. I should not mention. You should change the email. I can see how many of them failed.
Control. We have that in. No. Here we have this. What is control? So that's this right.
No, allocate two nodes and then show two nodes, and two nodes in there, and write into the text
So
file.
if we open this file, we can see how many nodes.
But you actually can see that.
Yeah, I see. I have this.
We have two nodes. And then,
Okay. Because I
it automatically
will.
produces.
Yeah. What do you think in school did I
Okay.
assign the two?
So your high example is MKL example. It's a
It's API. You
it's
just know. You just know.
It's using RStats, the surrounds built volume K stuff.
I think he's trying to run on memory. I'm trying to say it's running on memory or only running on standard.
I think it should be.
You probably on standard.
Standard period.
He got error when you run on memory.
Okay.
Maybe the no.
No, it's more interesting. Okay. Could be this.
Specifically two nodes in the code.
So this is
In the slum files.
Oh,
I thought the directories on Maverick were processed, they were accessible. Just maybe.
This is the work, the slash work directory.
Oh, not the home
It's not the
directory.
home.
You get SCPM.
Okay.
when you got an error, not the people show.
Okay.
That's right. So,
Okay, so is this is that a requirement? Memory task. So does memory has MKL installed? It's better you just try this on some It's the same thing, just the SSH is MP. We use the same word file as the copy.
So use the MKL node?
And maybe, I think the error is not the error
Is
is.
there any modification or something complicated?
No, but it's compiled against MKL, so either you need to know some other language. But not someone is.
Try to log in the MP as log out.
Our user can see.
You need to copy it to
Yeah, you could copy once again. Yeah, how do you execute? Like this, so I have to use execute.
That's not
Oh, I see. Okay, so there's something I can yeah, function which is there's syntax that will require. Oh, I see. If I want to okay, it's fine. So you can have yeah. Yeah.
text or notepad or something, write that and just a little bit larger font.
Okay.
It's hard to see swiftly.
So open a new window.
Yeah, just do a notepad.
Okay.
Just
on Stampede, I don't have that allocation.
It should be the same allocation. Okay. Same like
Oh, training.
training HPC.
Training HPC. It says training tech.
You have to change this one. HPC will change HPC. I get there on to yeah, looking at change the yellow one, you can change the sequential. Oh, okay. It's the same. You have to actually these two machines. Yeah. These are two actually shared between two machines. The notice file actually automatically generated by the Slurm script.
So what do I need to run now?
So there's these.
Yeah, so this is the beginning, so I'm not.
So you have to submit this.
Oh, first I need to execute that. And how do I submit? Yeah. You can see it, but
Yes, so that's
actually when the system allocates those nodes, you write those node names. Okay. To actually so it was yes, use yeah. Oh, Sandy? Oh, I was on Meta. Is that a problem? Yeah, so I was on Meta. But now I need to copy it. Oh no, sorry, that is we're trying to get the same copy. Yeah. It was in the same.
I know it is actually. Yeah, this is. So when you run jobs in this way, you're spot where you're doing this node list trick, you actually have to run a workaround. See this file, this is a reuse directory. You actually have to load the modules you want and then save to an env.txt environment variable.
Oh yeah.
Because when you fire off those jobs over the sockets, the module environment is not loaded.
I see. I see. No.
It's trickier, but we need to take this out of training. We need to find a better fix for this. So
It's not that easy. The environment article is not probably. You could do that. You just environment article. You can hide that.
yeah, I don't think this is gonna work for anybody. Yeah, this particular thing, we just want to let them know. Maybe we can like send out next week. And then, yeah, that's what's going on here. I know I'd seen that before. So I shouldn't have realized. It doesn't work without doing this extra little trick. Probably for this, we want to highlight like our MPI, our MPI snows. That one takes care of all of the setting up the nodes and clusters for you. Right. I basically told them that online. I guess they'll be in that session.
So, same with like this local terms of connections. So the nodes, all the nodes
It's because we're doing socket connections as opposed to
So you have the node. So if we set the environment variables, It should.
Doesn't matter because when you spawn off that socket process, it doesn't have the same environment. It has a completely factory fresh.
So it's a section.
It's actually,
So the only way is
they set up modules specifically to work this way to try to get around another issues that other users were having, crashes and nodes. Because he did the trick. He provided this environment file here. I don't know if we remember setting this up, right? Can you leave that text? All right, because basically what you do is you set your environment exactly how you want it. You do like an export your whole environment, I forget the exact command, and it saves it to that file. And then in his, and then bash rc.
Remember one time we do the environment.
You gotta have that. Bash RC is the only thing that's going to be picked up on the module system. So sorry about that. I totally forgot about that.
Yeah, when I do the ECSF project, we set it up.
Yeah.
So you need to use
So you want Flash?
yes.
Yeah. So we'll just take your example code and rewrite it so that you use the RFS node, and then we can just send it to them.
Yeah, it works on
Students
the second is
there's
Actually works. Somebody just actually run the job.
I think it might actually not. It might actually. How long does the job supposed to take?
Can I take a see the result?
Parallel job's taking forever.
I
So that was basically status.
I think it's because of this.
There's no additional gap. So the sequential one. You can run the sequential one over there.
Yeah, so the parallel ones,
We'll try the parallel.
there's a way to make it work, but it's not really pretty. So we're going to send out a cleaner example. So don't waste any more time on this. Actually, technically, a good use case is you're going to run into these issues actually running those cases. Yeah, sorry about that. We'll send out a bit.
Yeah. There's another example.
Yeah.
So this is a job.
Yeah.
So submit is ice batch. So
I'm not going to say anything about that.
now we use some scripts. So you see this is jobs on the process.
Okay.
It is successful successfully submitted to queue.
Okay.
And do executions.
Good.
Hey, can you guys hear me now? Check it online. You guys still can't hear? Mute microphone. Oh, that's right. Okay.
We can see right here if you're screen. Well, introduce yourself. Yeah.
All right, so my name is David Walling. I work in the data group along with the rest of these guys that have been presenting today. A lot of what I do is spend time working with users, trying to scale their codes up on systems like Stampede and Maverick. And a lot of what we end up doing is first trying to figure out, where are the bottlenecks in their code. And in a lot of cases, probably the majority of cases, the way that people end up using R is that there's kind of one piece of the code that needs to run lots of different times, but is completely independent of all the other runs. So those are the type of situations where it really is easy to parallelize using the packages that we kind of looked at in the last session, the for each, the MCL apply, things like that. But in this talk is about how do you actually find those areas of the code so that you can then go and spread those out to many cores on many systems and essentially get all your science done much quicker. So in this talk, I'm going to address some kind of basic Linux tools that I actually like to use more than the R-specific tools that are available. These include things like mostly top, and then just understanding your system, how much memory you actually have there and how many cores, which seems kind of trivial, but if you don't know that, then you don't know how to optimally set up your code to make the most efficient use of that system. So I'll first talk about those basic Linux tools, and then I'll talk a little bit about the rprof package, which is now a standard part of the R installation. If you ever Google like R code profiling, it's the one you're going to find. There's lots of blog posts out there about it, and it works pretty well. It's still relatively new, so it's improving, but it is kind of difficult to use too. But we'll work through a couple of examples and kind of explore what exactly that package is doing and how to use it to help you find where these bottlenecks are. And then at the very end, I'll mention a couple of additional kind of low-level tools that if you're, say, developing a CRAN package and you want to share it with a bunch of other users and you really care about performance, then those tools are probably ones you want to take a look at. And in addition to that, some of the tools in R that I do like to use are just kind of the simple timings, right? I mean, a lot of times you start out working with your code in an interactive way, and you're just sitting there watching it run. It becomes pretty obvious right away where the kind of bottlenecks are in your code. And then you can go in and start wrapping pieces of that code in these kind of simple timing commands to let you know exactly how long they're taking. So basic Linux tools. The first one is just, how do you actually know when you're on a given node on a system how many cores there are on that node? We run heterogeneous-based systems here at TAC now. So Stampede, for instance, has several different types of nodes available on it. Generally, those are controlled through the queuing system. So if you say, I want a large memory node, you would submit to the large memory queue. If you wanted a normal node, the normal queue, so on and so forth. And each of those nodes, in addition to maybe having different amounts of RAM, may actually have a different number of cores on the system. So on Linux, this is the kind of standard way that you can check, well, for this given node, how many cores are actually on the system. You just execute this cat command, to this file that should always be pretty much in the same place on any Linux system you're on. But it's basically proc CPU info. What you're going to get is this type of output. And you're going to see at the end that the last processor ID is 15. Those processors are indexed from 0, so that basically means that you have 16 cores on your system. So theoretically, you should be able to run 16 simultaneous R processes on that node. If you do any more, then those processes would just be fighting over resources essentially, so you would actually degrade the performance of your code. Exact same type of procedure for figuring out how much memory you have. And what you really care about, and I should be pointing with this because I have people online, what you really care about is this mem total. So here this is in kilobytes, so I see that this Stampede normal Q node has 32 gigabytes of memory available to it. So pretty simple commands, but I know a lot of people come to TAC being previous Windows users of R. And when you do come to TAC or really any other supercomputing center, you are going to be working in a Linux environment. So kind of knowing some of these basic tools should be helpful for you. So cat proc mem info will tell you how much memory is on the system, but if you actually want to look and see how much memory is free at a given point in time, you can run this free-m command. Essentially, it's going to show you that I have 32 gigabytes of memory total. Currently, about 4 gigabytes of that is being used, and I have 28 gigs free at any given time. So certainly, there's always going to be, even on the back-end compute nodes, the operating system is going to take a certain amount of memory. And as Riju mentioned, I believe, as you're thinking about how many processes I can actually run on a system, once you figure out how much memory a single process takes, you need to kind of do a quick calculation to determine how many you can actually run, and you should base that off of basically taking 70% of the total memory available. That other 30% is what's going to be available for things like the operating system, and also for doing a lot of the R internals where it's copying memory around. It just needs a little bit of extra swap space. So if you go over about 70%, you may start actually running into a lot of issues like cache misses, and things like that. So rule of thumb there, take this number, multiply by 0.7, and that's kind of how much working memory you have to use in your R code. The one I actually use the most to see what my R code, what kind of resources it's actually using, is top. And we'll kind of look at what the output of that looks like. But as our example case, very similar to what we did in the last section, we have this kind of example myproc function that we're going to use. So essentially, it's just going to create a vector of ones of a certain size, and then it's going to sum up those entries and print out the output. So when you run top in the terminal, it's going to sit there and continually update the output, but it's essentially going to show a list of all the current processes running, how much memory that process is using as a percentage of total available, how much CPU percentage it's using as a total of all available, and then some, similar to free.m, some stats on current memory, how much is being used, how much is actually free at the particular moment. The main ones that you're going to care about are memory percentage and CPU percentage. Kind of a what can be a little bit strange is that CPU, if it's at 100% for a given process, that means it's using 100% of a single core. You can actually see that number go over 100% if your code, that process that's using that core, can be doing multi-threading. Usually with R codes, you don't see it go over 100% because the R process kind of caps it to a single core. What you will see though, and what you want to see when you start doing, I shouldn't point, sorry, when you start doing parallel R processes, is essentially you want all of your R procs showing up at 100% essentially. That means that they're more or less being used all the time and being efficient users of the system. So there's tons of text out there on how to interpret top. Again, the things you're most interested in is the total memory available, how much is being used at a particular time, how much is currently free. Obviously, you want that to be greater than 0. You can actually crash the node if you end up trying to grab all the memory and it can't do anything else. So you'll start seeing some memory-related scary error messages in the output, essentially. When you're actually running on Stampede and Maverick, when you do launch your R processes, those processes will always be owned by your user account, so that makes it a handy way to kind of filter out all the processes that you don't have any control over. And we'll kind of look at examples of how to do that. So one thing to notice, like as you guys went through examples of launching jobs through the batch system, you may have noticed when you ran commands like sq-u, your username, you could actually get the list of nodes that job is running on the back end. Only when you have an active job running on the back end are you allowed to actually log into those nodes. So here I can see that I have a job running on C558403. So that actually allows me to SSH from the login node into that back end node, so that I can start using things like top and some of the other tools to actually see what's going on.
But that was one processor. If it was more than one processor?
More than one node?
Yeah.
Yeah, you would have to. Well, I'm going to show you an easier way to do it anyway. For little low-level stuff, I will go in there and do that, but you can actually call system commands directly from R. So you can just have it, so you can call top essentially from your R script, and it'll give you that information and spit it to your output file essentially. So that's kind of the preferred way to do it now. So here I'm going to call my proc command. I'm going to call sys.getPID, which is going to return the process. Oops, sorry. Back up. We get the process ID of my running job, and then I can call top, and then if I pass in these particular parameters to top, it'll only return my processes, and I can change how frequently it updates. Or actually, you set -n equals 1 means it won't try to update itself, because we just want to grab the output essentially and spit it out in our R console. So here we see, this is actually I ran on my laptop, so you see all these other non-R related processes, but I can look for 10.243 here and see that my R process kind of shows up down there. Again, when you're actually running on the back-end node, certainly you won't have things like Firefox and all these other Fedora specific processes running, so it's a little easier to weed those out. And usually by providing this -u user, the only processes you'll see are going to be your R processes. I'm sure you can, yeah. Would you know, Amit, didn't you tell me how to do that at one point? Can you just run top with just providing the PID? Yeah, so that's another option as well. You don't want to do that, though, if you are running parallel, because the process ID that this returns will be the master script, and all those spawn processes wouldn't show up in that case. So it's better to just pass in -u, your username. Well, in this case, it's using the environment variable $user. So that's kind of the Linux tools. Again, I use top probably more than anything else. Second to that is actually time pieces of the code that I'm interested in. And there's kind of two main ways to do that. The most straightforward is, again, part of R's built-in core package is system.time. Essentially, it works like this. If you have a particular function, you just wrap that function call in system.time, and it'll give you the timing output. What you're most interested in here is obviously elapsed time is the total wall clock time, and then user time is how much of that wall clock time is actually being used by your user processes. So if I had perhaps like a sleep statement in my myproc, my user time may be half of the total elapsed time. Generally, you want to see those be pretty equal. Otherwise, your code's just sitting idle for some reason for a long time. You may want to go investigate why. So that's just kind of something to be aware of. Now, system time is convenient for timing like one specific function, but it gets to be kind of difficult to write your code in such a way that that's really that useful. A lot of times you want to time just like subsections of a particular function. And the way you can do that is just to wrap that piece of the code in two statements. First, you call proc.time, which just saves the current time. Run whatever code you want to. And then at the end of that section of code, you just do proc.time minus what you had saved, and it essentially gives you the same information. So that allows you to just kind of go in there and just pick out very small subsections of the code that you want to time and to do it that way. It's just a little more convenient in my experience than using things like system.time, where you'd have to actually write the code in such a way that it's easy to call through that mechanism. rprof is that package I was telling you about. I think it started out as a third-party package that eventually got wrapped into the core R deployment. And it's still kind of a work in progress a little bit. But at the same time, it is pretty powerful. So this, to demonstrate how to use it, essentially what you do is you call rprof, give it a file name to store some information in, and then you can set the interval setting. I'll talk about a little bit more in detail why you might want to do that in a bit. I need to quit clicking on that. Essentially, similar to like the timing, you just wrap whatever code you want to be profiled in these two statements. So rprof initialize basically, and then rprof null, which basically ends the profiling. And all that is going to do is sit there and poll by default every 0.02 seconds and see where your process is in the code. And it's going to save all that information into this rprof.out file. So to actually make any sense of that, you're going to run this summary rprof command and pass it in that file name, and it'll give you a nice little summary of what's going on. So if we go back and look at essentially, we create a vector, we do a loop, and we repeatedly call sum plus whatever the particular vector value is at that time. So we can compare that with the output from rprof. The first section essentially shows, for a given process, it'll show the total time it's been in that process, and then how much of that time was spent in the process itself versus kind of sub-functions that it ended up calling. So in this case, 90% of the time was spent doing stuff directly in my proc. 10% of the time was spent doing stuff in what it considers a sub-function, which is the core plus function, essentially. These numbers essentially kind of break that up a little bit further, so you can see that this is always confusing. This is why I don't like to use this much, because of how the output comes out. But essentially, this just kind of inverts how you're looking at it. So I can see again that this just breaks it down to basically only what happened in my proc versus only what happened within the plus function. So a total of 3 seconds was spent in my proc. A total of 0.29 seconds was spent in the plus function, for a total of about 3.5 seconds total runtime. Just a slightly different way of looking at it. So go on down. Arguably, to make the output a little bit easier to read, you can now tell it to do line profiling. So to turn that on, you would just rerun your profiling and pass it to command line profiling equals true. And then in your summary rprof, you need to pass lines equals show. What's a little bit wonky about this is that the lines are always going to be relative to the function. So you actually have to go back and look at the function. Added the line numbers here. You don't have that convenience. There's no automatic way to generate those line numbers, but essentially it's saying that all of our time is spent in line 3, line 7, and then line 6. It just helps you figure out exactly where in that process your time is being spent. So if we go back and compare that again to doing it without line profiling, it's only looking at the function name, not necessarily where in that function is doing stuff. So So line profiling is probably the preferred way to go. It's just you kind of have to work around this issue of well, what line is it actually referring to? And it's kind of hard to keep straight sometimes. If I had actually called like a function, a full sub-function, it would print like that function's name dot line 7 of that function. So you just kind of have to get used to the output, but you can get to the meat of what you want to do. So again, we're looking at lines 7, 6, and 3. Here we see our dominant time is in line 7. And we see that that's the actual plus assignment. So this is a really dirty way of doing it, because not only does it have to execute an addition, it actually has to update the value as well. So it's just a really inefficient way of doing things, and we kind of see that from our profile. The next most expensive part of the code is the line 6, and we see that that's actually the for loop. And as we'll come to see, one of the first things people tell you to do to speed up your R code is to get rid of all the for loops. That's a bit of an oversimplification. You can certainly use for loops if you do it in an intelligent way, but you don't want to be doing things like updating memory locations within a for loop. That's just highly inefficient. And we'll see better ways of doing it here shortly. And then finally, line 3 was just that basically creating that initial vector. And we see that that pales in comparison to these other things. So what we'd want to do is tackle that sum, having to do that memory kind of reallocation in every iteration of the for loop. I'll just mention this one. I haven't played with this one as much, but just within the past year, they actually added memory profiling to rprof as well. So very similar to line profiling, you can turn it on by passing in this parameter. And then there's a couple of options of how you output the statistics that it generates. I do add this warning here, though, is that there's some technical reasons why this isn't necessarily going to be accurate. When I'm really worried about memory issues, I prefer to go in there and use top and actually look at what the Linux system information is giving me about those processes. But it is there. I expect this to get better. And I think there's some other third-party packages that are trying to address these situations as well. So now that we kind of, so actually before I move on, I wanted to actually show you, just to give you a little bit better understanding of what rprof does. So here's a local version of my RStudio. So if I look at that rprof output, again, all I'm seeing is that it just captures what function it happened to be in at the particular time when it polled. So if you have something that runs like really fast and is less than the default of 0.02 seconds, it would never show up here, right? So that's why you can actually control the interval setting. 1 second. As I did here. But I'd argue if anything is finishing within 0.02 seconds, you probably don't care about it anyway. So yeah, so now that we know that that loop is basically where all our time is being spent in our code, we think about ways that we can get rid of it. One of the things about R that is kind of hard for some people to learn, especially if they're coming from a different programming language like a Python or Java or even C, is to always kind of be thinking in vectors. And so when people say, well, get rid of your loops in R and vectorize them, what that means is that most functions, especially those in the core packages, always know how to intelligently handle vectors when they're passed in as arguments. So for example, we could replace that entire for each loop by just calling sum over that vector. And it's essentially going to produce the same type of output. And another dirty secret about R is that really under the hood, especially a lot of these core packages, it ends up running C anyway, right? It's just a big wrapper around some of these lower level codes. And that's a good thing because C is harder to program in. R is really easy to program in, but you can still utilize some of the speed benefits of the lower level languages with a much nicer interface to it. So essentially that's what's going to happen with this particular function. And just doing a simple timing, we can see how drastically different the speed up can be, right? So going from a loop that took almost 3 seconds to do a million, iterate over a million elements is now less than a tenth of a second, essentially. So that just kind of highlights why people always say, get rid of your for loops, try to think in vectors, vectorize everything that you can. You can get some pretty impressive speed ups just from doing that. So finally, just a couple of points that I would highlight just from working with users and kind of spending a lot of time looking at these type of issues. The fact is that everybody who's ever came to TAC, and I've worked with, has said, hey, I'm trying to use this R code. I want to scale it up on Stampede or Maverick. It's never just one simple script, right? It's usually about 10 scripts. They all call each other. They're all calling third-party packages that you don't really have any control over. A lot of those third-party packages are calling C and Fortran under the hood, so on and so forth. So it can be really daunting to try to find a bottleneck in such a cobweb of code. It makes it really easy to develop the code because you just get to reuse what everybody else has done, but to actually go in and figure out where the bottlenecks might be can be challenging. So tips for actually trying to do that is mainly think about where are you doing certain tasks that you need to do a bunch of times and that are completely independent of each other. Because those are the ones that are ripe for embarrassingly parallel type of approaches that almost all of the parallel packages in R are designed to enable, essentially. The second main thing is when you start to do profiling, if your job's taking 2 hours and you want to profile it, you don't want to have to wait 2 hours to look at the profile, realize you messed something up, and then rerun it. If at all possible, reduce the amount of input to your job. Use sampling on a huge data set to kind of give a proxy run of that job that can finish within a couple of minutes or even seconds if possible, and just profile that. But generally speaking, the same bottlenecks that you find in those really small, quick profiling runs are going to be the same that would happen in your 2 hour, 2 day, long runs as well. So that allows you to just iterate really fast, plug in different timings in different parts of the code to kind of whittle down to where exactly your bottlenecks are in kind of an efficient fashion. And then finally, I wanted to highlight this as part of the PBD R project. If you actually really care about things like cache misses and how exactly your code is efficiently using memory or not, there's actually a really nice package from those guys that uses PAPI. To do really more advanced code profiling for you. This only is going to work on a Linux system, but if you're running a TAC, you'll be running on a Linux system. And there's this really good blog posts about it here on our bloggers that I wanted to share with you guys. But it'll essentially show you how drastically inefficient some R code can be. And if you are trying to package up your code for reuse by other people, it's worth taking a look at some of these lower level packages. With 7,000 packages available in CRAN, there's several more that are kind of dedicated to this task of trying to figure out where your code is slow. But again, the dominant ones you're going to see are RProf. There's a couple new ones like this PBD PAPI, and so just kind of be aware of those. And that's really all I had. I would say that if you're at that point where your job's taking 6 days to run on your own lab's computer and you're ready to move over to TAC, please do get in contact with us. We love to work closely with users to try to scale their code up on our systems. We're really trying to grow the R community. It's a really great community to work with, and yeah, we look forward to talking with you guys. Thanks for coming today. I'm sorry about the technical glitches that we had, and as far as the example that we were running in the parallel section, we'll send out an updated version of that to the mailing list. It's actually a valid example. It's just one other step that you have to do to make it work, and I'll document it. what that is, because it actually is a very powerful way to have control over exactly how your job's going to run on our systems and how you break up those parallel tasks to multiple nodes. So I think, Jason, do you have any other kind of bookkeeping stuff you want to do as far as surveys or anything like that?
I'll be sending out a survey as well with some feedback on the material presented.
So for the people online, Jason Allison will be sending out an email with a link to a survey and some additional resources for you guys. And yeah, again, we thank you guys for coming. Hope you have a great weekend. Leave that up for now.
Question.
Mm-hmm.
Some of the slides in some of the presentations didn't match what the downloads were off the website. Are you going to update those for us? Or?
Yeah, we'll repackage those and put them up on in the course materials page.
Yeah. Okay. And notification when that's done, just email or just keep checking for it, or?
Yeah, we're doing this. Let's wait and send that email out after we do that. We'll get that done pretty quickly. I think we have it all compiled now. So.
Okay, perfect. Thank you.
It probably won't be till Monday or Tuesday before I send out the other example script.
Yeah, that's fine.
But yeah, we'll get the materials up. Oh, I did want to mention too, the allocation that you guys have been running against. Again, there's one for our TAC users who came through TAC, and there's one for the Exceed users. That'll actually be active for at least the next 7 days, so you can continue to play, around on Stampede and Maverick and start to learn the systems.
If they have any challenges with, the business portal not showing that, just have them, contact me. I'll get this portal added and take a look at it.
Yeah, absolutely. So if you're still having any issues running jobs, just email data@TAC and we'll help you out.
I have a generic question that, since I missed the beginning part of this afternoon, so it seems that knowledge of parallel programming, like message passing and MPI, is helpful because in some sense it's the same constructs. Is that correct?
I would argue that most of the code I've seen, you wouldn't need to know MPI. MPI gives you extreme control over exactly how you talk to different processes.
Yeah.
Most of what I see in R is embarrassingly primitive, so you don't actually have to pass messages back and forth from process to process. It's just each process is run by itself, finishes the next process.
So what about collecting? I guess when a processor does a calculation, it's local to that memory, right?
Yes.
So then it needs to be sent to the master, right?
Right. So things like for each and CLFI, they take care of that for you. What you don't have is each of those processes talking to each other. They only have to talk back to the master and basically collect its results in a list at the end of the job.
So is that because that's the type of parallelism that makes sense for data analysis, the ones that are embarrassingly parallel, or is it you're saying that R doesn't do the internal processor to processor?
You can, but that's not necessarily any easier in R than it would be if you were writing it in C.
So we have separate tuning for the API in general.
Yeah.
But if you are down to that levels, I wouldn't suggest you still working with R. You can work with C program like into API directly. For R, there's a package called RMPI. A lot of the things is built on top of the RMPI. So the RMPI package is derived the wrapper over the C MPI libraries that we build on the